Alright, we're going to show that every irreducible representation of G is contained in a representation induced by an irreducible representation of H. And that's all that is asked of us for this problem. And there's nothing else. There's no other things that this problem asks us to do. Certainly nothing that I would have just seen now and not realized and realized that I had not prepared a proof for. Nope, there's no other parts to this. And I'm sure if there were any parts, they wouldn't be too hard to conclude from the first part, but that doesn't matter because there's nothing else. It's just the first part. So let's start. Let rho be an irreducible representation of G. Okay, we know rho is a sub-representation of the regular representation of G, rho reg. We will denote this rho reg comma G. This is the regular representation of G. Okay. Now this implies that the inner product of chi rho with chi reg G is greater than or equal to 1, because this inner product is the number of times that chi reg G contains chi rho. No, the number of times that the regular representation of G contains rho, and it contains it at least once because it contains it once, but it could contain it more than one time. Next, let rho reg H, so this is the regular representation of H, and that's why I have this extra G and H here. That's why I included that, so that we can distinguish between the two. Write this as the direct sum from 1 to n of theta I, where theta I is irreducible. Then rho reg G, we know that this is the induced representation from H to G of the regular representation of H. But what is this? This then is the induced of the direct sum of the theta i's because of the definition. But we can bring this direct sum out. I forget if this is something that I proved in my class or if Serre proves this in the text. It's something I should know, but I don't know it right now. But in either case, you can bring this direct sum out. Therefore, chi rho reg G is just chi rho, and then the sum from 1 to n of the induced from H to G of chi theta I, because this is just the character of the induced, because you write the regular representation like this direct sum, and then when you take the character of that, you just get the sum of these things. And so this is equal to, now we can bring this sum out, chi rho, and now the induced from H to G of chi theta I. Okay. But chi rho Yeah, this is probably the best way to do it. But chi rho chi reg g is greater than or equal to 1. We proved that already. So it must be that that there exists an I such that chi rho induced from H to G of chi theta I is greater than or equal to 1. Because this sum, each of these direct products is going to be some integer greater than or equal to 0. And we know that if we sum these all together, then it gives us a number that's greater than or equal to 1. So at least one of these must be greater than or equal to 1. And then this tells us precisely that... so this is the... Now, what is this direct product? This direct product is... precisely the multiplicity of rho in the induced representation from H to G of theta I, and that means precisely that rho is contained in the representation induced by theta I, i.e., it's contained in a representation which is induced by an irreducible representation of H, namely induced by the irreducible representation theta I of H. And so I'm going to fit this. The result follows. Okay, and there we go. This completes this exercise.